very good morning. Today I will start my lecture on Vlsi and microelectronics, and I will try to cover the first module. And here I have written some points, some outline points that will cover which are the portions I am going to teach you in my lecture. See that the first point is design flow. The second point is Y chart. Third point is the design parameters. The fourth point is how to design using CMOS. And why using CMOS, that portion I have already covered in my introduction class. And the last portion, which is the important portion, and it's a beginning portion of designing part, that is some basic design rules with example. And from this portion, we will start that how to design, what are the design rules, how to connect the NMOS and PMOS in the CMOS structure, everything. So I have designed this outline in my own way because I should start with the MOSFET structure. But I think that you should start with a very interesting thing that in that way it will enhance the confidence in yourself. So that's why I will start from some of the design part, and by covering this module I will definitely enter to the MOSFET basics, and that I promised in my introduction class that I will teach you that the basics of MOSFET, the basics of current voltage relationship, and the basic of MOSFET scaling, how MOSFET is acting as a switch, everything. And all about MOSFET will be taught by myself in my next lecture. But before that, I will start with some interesting part so that you will be happy to understand that yes, it is the design rule, and why it is CMOS, and why VLSI and everything, right? Okay, so let's start. I will start from the design flow, because in my introduction class I have already told that all the design will be using CMOS. And why CMOS? Again, I am repeating that the area requirement is less, it is more efficient, current drawn is very less, power drawn is very less, and last but not the least, it is cost effective. Okay, so all these parameters are incorporated with CMOS structure, and that's why CMOS is chosen for the main design block of any VLSI circuits. And beside that, I must say that there are two parts of VLSI. One is digital VLSI and other one is your analog VLSI. But design flow is common for whether it is analog and whether it is digital, right? So it is a generalized part that I will describe in my introduction section, and after that we will gradually enter into the digital domain, and after that we will enter into the analog domain, right? Okay, so let's start with VLSI design flow, and it is a very basic. Please think in your own way. I am explaining just like a story. Okay, so nothing complex is there, all are simple. Please think in your own way and write in your own way, not copy. Okay, so let's start with the VLSI design flow. I have drawn the structure because it is impossible to draw the each and every block and explain parallelly. So that's why I have designed the very basic design flow, okay, of your VLSI design, and I will share the hard copy, the not only hard copy, the soft copy of this in a PDF format. I think that there will be no issue. Okay, so let's start. See, this is a VLSI design flow, right? And that I gave some idea in my introduction class, that whenever we are going to start any design, we have to verify that what is the system specification, what is the design specification, how to design, what is the input and what is the output, how it works, everything. And after that we will go for the logic design or schematic design part, right? Okay, so first just see the left hand side. I have segregated the whole design flow into some domain, that is the behavior representation, logic gate level representation, circuit level representation, and layout representation. I think that these 4 points will clear your concept, that whole design flow, how it is segregated into the various section. Okay, so first it's behavior representation, because before going to the design part, we have to check the behavior. Behavior means the input and output relationship. What is the input and what is the output, what is the system specification, what is the transfer function, and everything, right? So first of all I will check the behavior, then I will check that what are the basic building blocks, how it is designed, okay, how it is developed, and what is the logic gate level representation. That will be done in the software part. And after that it is the circuit level representation, it will be the circuit level representation. And then we will verify the circuit. After making the circuit, we will verify that whether the input and output are mismatching or not, or matching or not. And then we will go for the physical design. Physical design means in the IC form, the layout representation. And after that it will be go for fabrication, testing, and packaging, everything. Okay, so first it is the system verification, then it is architecture design, and then it is the functional verification. In which system I am going to design, which is the basic architecture I am going to design, and which is the functional verification, and which is the function means the operating principle, how it function. Then all these will be clear in a behavioral domain, in a behavioral representation, right? Okay, and after it is over, it's clear, then we will go for logic design. What logic will be used to design this system, to design this behavior, right, to design this function. So we have to make a very clear view of the logical part. Logical verification is over. After that all this logic, if it is suppose if it is a NOR gate, or very very simple, if it is a XOR gate, what is the logic part, what is the logical part? We know that is 0 0 is 0 and 1 1 is 0 whenever the inputs are giving in a similar, okay, both are similar. So if it is 0 0, then the output will be 0, and if it is 1 1, then the output will be 1. If it is 0 1, if there is any mismatch in the input, the output will be non-zero, right? So 0 1 1 1 0 again 1. So this is the logic. We have to develop the logic, right? Otherwise more components will be needed, more area will be involved, and the circuit will be slow. So the logic is developed first after the behavioral representation, and based on that logic we will go for circuit level representation, right? We have to reduce the circuit level representation, we have to reduce the logic, we have to use some logic to reduce the circuit level representation. And how it is done, I will definitely show with the example later. And it's all about the VLSI design flow. In the digital part you will get understand everything, that how to reduce the logic, how to what are the rules for reduction the logic, everything, how to reduce the truth table, everything. So this all belongs to your logic design and logical verification. After that, so these two blocks are interconnected, and that's why I am giving that arrow. Okay, after that, whenever the logic is developed, yes, we will go for circuit level representation, and this is a circuit design that is known as a schematic, and it will be done in the software part. For your VLSI, there are various types of software, that is Xilinx software, T-Spice software, and that is used in your lab, but it is very costly, right? So these are the software section that is used in the industry before going to the fabrication. So all these verification are done run in a software, and after that we will go for simulation, then the result analysis, mean the output analysis, the waveform checking. Okay, all if it is all clear, then we will go for fabrication. So this is all about your logical design and circuit design, circuit verification, right? Okay, so if we all confidently pass every level, then we will go for physical design and layout verification. Physical design and layout verification, yes, it is the mother, it is the core section of any VLSI design, because physical design means how to feasible, how an IC is feasible, becomes feasible. So feasible means the layout and floor planning, the module replacement, everything will be there. There is some new terms I am again repeating, so all will be new terms will be taught by me, by myself obviously. And this is the physical design and layout verification, this is the fabrication part. Okay, so how the we will go from the basic substrate, then the another layer is formed, then another layer is formed. So all these all about your physical design. So and that portion I have represented over here, that is layout representation. So you have came to know with a new term, that is layout. Okay, so this section, that is we are going for fabrication, and before going the fabrication, the process is known as the layout design and layout verification. And after fabrication, fabrication is not so easy, because in this fabrication there are so many process, so many steps. And after fabrication is okay, then we will go for testing. If it is okay, then we will go for packaging and commercial responsibilities. Alright, so this is the overall VLSI design flow. Is a very simplified version, but there is a complex version also that will be explained later. Okay, and this is a very important question that also came in this in the previous semester also. Is a very important question of any semester. Okay, so this is a VLSI design flow but simplified version. And again important related to design is that is Y chart that I told you in the introduction class, that is all these design flow can be defined just simple Y structure. Okay, so it's upon the scientist, a Chinese scientist who invented this structure, and this is nothing but Y. Y means there are there are three domain, this domain, this domain, and this domain. And we will definitely start from our behavioral domain that we have already explained in the previous section. The behavioral domain, then structural domain, and lastly it is geometrical layout domain. Okay, why we will start from behavioral domain? Because we have to know the behavior, we have to know the what is input and what is output. Okay, so based on that we will go for structure. Yes, this is needed, this is not needed, this gate is needed, this ALU is needed, this processor is needed, everything, the transistor is needed. So this is a structural part, that what will be the building blocks and which components will be used to build up the structure. So after knowing the behavior, we will enter the structural domain, and whenever the structural domain is complete, then we will go for geometrical layout domain. And this geometrical layout domain it's wholly includes the VLSI design, and that is I have written some terms over here. That is I am starting from the beginning, that is masking, cell placement, then it is module placement, and then it is chip floor planning. Okay, masking means, masking it's a process of fabrication that will be explained. Cell placement means if the substrate, we are knowing the we all know the substrate is nothing but a floor. Okay, we have a floor in our house, so substrate will be treated as a floor, and that floor will be divided into some blocks, and in that blocks the modules will be placed. Okay, and which module will be placed in which blocks, that is all about from the logical design part. Okay, and that logical design, that engineer will decide that which block will be placed in which module. Okay, so the overall floor of the substrate will be divided into blocks, and the modules will be placed in that blocks, and after the module will be placed, it will be interconnected. Okay, and not because until and unless we are not doing the interconnection in between the modules, the overall connection is not there and we will not get the output. So the internal connection is very much necessary, and that is named as your locality. Okay, so from this design part, we will define three important design parameters that I am coming to later. But before going that, the last part is chief floor planning. Chief floor planning means the whenever I see we are going to bake, but before making we have to make the layer by layer decomposition. Okay, so the total process is known as your floor planning, because we are substrate, this is a floor, and which the division, module placement, interconnection, everything is known as planning, and overall process is known as your chief floor planning. Okay, so this is all about your VLSI design, but all will be explained in detail. Okay, and these all process incorporates the geometrical layout domain. This geometrical layout domain, whenever it is complete, then we will go for fabrication. Now go for fabrication in the industry, in the lab. Okay, and please see the behavioral domain. In behavioral domain, how can you check the behavior? Obviously it's showing any algorithm, showing any truth table, showing any boolean expression, everything, right? And how can we define the structural domain? Yes, by using the component. It may be transistor, it may be leaf cell, it may be register, maybe ALU, maybe processor, everything, but all these have been generalized in this Y structure, just to give you an idea that how this VLSI designing is happening in the industry. This is a very general part, and it is a very important structure. It's a very beginning of your VLSI design flow, and this is very important question, that is define Y chart. Okay, Y means there are three domain: behavioral, structural, and obviously the geometrical. Because until and unless we don't know the behavior, we will be not able to develop the structure, and if the structure is not developed, then we will be unable to go for fabrication. So each domain are interrelated with each other. Okay, and lastly, in the design section, I must explain the three terms that I have already used in this chief floor planning and module placement. That is your first design parameter is regularity. Regularity means the total large structure is decomposed into the similar blocks as much as possible, and this is the process of regularity. Okay, for example, design of an array structure into consisting of some identical cells. Okay, or we all have a floor in our house, there is a mosaic. Okay, and there some blocks are there, we can color everything, we can design everything, and that is similar to the regularity also. A large structure is divided into the smaller blocks that should be similar and as much as possible. Okay, whenever we have a division, then the next parameter is modularity. Modularity means the module, the each and every module means suppose we have to incorporate some transistors, so each and every transistors will be treated as a module 1, module 2, and so on. So that modules will be placed into that functional blocks that is already done in the regularity section. So that defines the various functional blocks which make up the larger system must have well-defined function and interfaces. Why it is called interfaces? Because each and every block are connected each other, and the connection in between them is known as the interface, and each modules are identical in nature. Otherwise we can't be able to adjust all the blocks in that floor plan. Okay, so it must be similarity in nature. And what is the locality? Locality that I mentioned in the previous part, that whenever that all blocks are placed, all modules are placed, must ensure that they are connected each other. Okay, so ensure the connections that are mostly between the neighboring modules. We know the neighboring modules, the module and the beside module is known as the neighboring module, and avoid the long distance connection as much as possible. Because the area is small, the modules will be adjusted in this smaller area, so we have to avoid the long distance connection as much as possible, and this making the overall connection in between the modules, in between the blocks, is known as your locality. So three important design parameters are there, that is regularity, modularity, and locality. But it is not the final one. We will again discuss there are different types of design rules, a lambda based rule, stick diagram, everything that is necessary for VLSI design. But I should come to that portion one by one. But before going to that, we have to know the very basic part that is needed for your VLSI design flow, and this is a 3 part. Okay, so in this design section we have covered that the VLSI design flow in a simplified version, the Y chart, and again these design parameters. Okay, in my next lecture I will cover that interesting thing, that how to design CMOS, how many NMOS and PMOS will be connected based on which rule, and different kinds of rules are there that will be introduced in my next lecture. So thank you.